This is the first lecture in the Chapter 12 Modern Chemistry book. In this lecture, we are going to be reviewing a little bit about solutions and how they form, and then we're going to be expanding on that knowledge with all the things we've learned about different ionic combinations and ways that compounds form. So to review, remember that mixtures are any substance that contains multiple parts or components. I have some examples here of a variety of the ways that mixtures can look. These are all kind of mainstream examples rather than chemical examples, but you can see that there are homogeneous mixtures, or those that have fairly uniformly distributed materials, so it all looks pretty much the same. We've got milk, we've got Kool-Aid. And then there are heterogeneous mixtures where you can see the component parts, or at least some of them, and depending on the part of the mixture that you're looking at, you can see completely different components and completely different compositions. So for instance, I guess that's like a chicken soup or something down here on the left, and then we've got soil on the right. And there is such a huge variety of ways that soil can appear. It's a really good example of a heterogeneous mixture. Remember that solutions are a mixture that is pretty uniform, at least uniform to the naked eye, and it involves at least two substances, and both of those substances are in a single phase. It is possible to have mixtures in any one of the phases of matter, at least solid, liquid, and gas. Those are the three we're going to focus on. And there are very predictable parts to every solution. The substance that's being dissolved is called the solute. And remember that the solute is usually the substance or the component that is lesser in the solution. So if you have two components, the solute is usually less than half of the total, and the solvent is usually more than half of the total, and it is the substance doing the dissolving. So in our example from the previous page where we had Kool-Aid, for example, right, we've got our picture of Kool-Aid, and so in this case our solvent would be water and our solute would be the Kool-Aid flavoring. There's less of the Kool-Aid mix than compared to the water overall. Another couple of terms that we'll use quite a lot, rather than saying dissolved, in chemistry we usually use the term soluble, and that means that the material or the substance is capable of being dissolved. When it is dissolved, we generally will get uniform distribution throughout the solution. So again, we'll stick with our Kool-Aid example. When the mix dissolves in the Kool-Aid, it becomes uniformly distributed. So you get this complete solution that looks virtually identical no matter where you happen to be observing the solution at any given time. There are some other types of mixtures that we haven't really dealt with, but they're pretty interesting. The first is called a suspension. And a suspension is when you have particles that will dissolve or are soluble if they're kind of forced to be. So perhaps the solution is heated, or it is stirred, or it's mixed, or it's agitated in some way. But with a suspension, the key is that if the solution is left to its own devices, if it is just left alone, then the particles themselves will fall out of solution. They will be too large to remain uniformly distributed. And this usually involves particles that are over 1,000 nanometers in diameter. And that is, keep in mind, that is really, really tiny. A nanometer is 1 times 10 to the negative 9 meters, right? So we're dealing with a very, very, very small particle still in most cases, but those particles are in fact too large to remain completely uniformly soluble in most liquids. The second mixture type is called a colloid, and this is kind of the middle ground between a pure solution and a suspension. So what generally happens is you get more medium-sized particles. So we're dealing with anything from about 1 to 1,000 nanometers. And these particles do tend to stay pretty evenly dispersed. They're fairly uniform, but they're slightly larger. And so what happens, this is really interesting, and milk is a good example of a colloid. When we are viewing these types of mixtures with the naked eye, it looks as though everything is uniformly distributed. There's no way to really see these larger particles. But if you shine a beam of light through them, and you can kind of see this in the picture below, we've got a car with its headlights on. So generally speaking, if you're looking at a car from the side, you're perpendicular to the car, you won't be able to see the headlights. You can only see the headlights if they are directly in front of you. When light is being passed through a colloid, what ends up happening is the photons of light are bounced off the medium-sized particles within the solution. And so you get this beam of light that you can see from the side, which is an observation called the Tyndall effect. It's pretty interesting. And this picture illustrates that. Fog is an example of a colloid, believe it or not. It's a colloid in the gaseous phase rather than in liquid phase. And so there are particles of probably water and perhaps even smog and dust and things in this colloid mixture of fog. And so you see the headlight beams bouncing off of those particles from the side. That tells us that we're dealing with a colloid. If this were a pure solution, the light would pass straight through. The particles are far too small to scatter light, and you wouldn't see them at all. Some other terms that you might hear, not so much in chemistry, but in just other aspects of life. Other terms that describe colloids are emulsions or foam. If you watch cooking shows or you like to cook yourself, you'll hear those terms quite a lot in food science. And those just mean mixtures where there are particles kind of suspended in a solution or in another medium that has this variety of particle sizes. Okay, so the last little detail about solutions that we're going to talk about today are some of the characteristics that we use to describe the solute itself. So when we add a solute to a solvent, assuming that solute breaks down or dissolves, if it is able to conduct electricity, and you can see that kind of in this picture down here, if the solute is able to conduct electricity, then we call it an electrolyte. That means it has charged particles. Electricity requires the presence of charged particles. And so all of the soluble ions, all of the ions that we've talked about that have the ability to dissolve in water, when they do so, and salt, table salt is a really good example of this. When table salt is added to water, it breaks apart into its component ions. And the presence of these positive and negative charges allows for the really easy and rapid conduction of electricity through the water itself. Electricity needs to jump. It jumps from positive to negative to positive to negative. And so you need these charged particles in order for the electricity to move through the substance. There are lots is a very poor scientific word. There are many solutes that do not conduct electricity. These are primarily non-ionic compounds, things like sugar. Let's use table sugar as an example. Here we go. So with table sugar, when it breaks down, it also breaks down into component parts. You get some carbons, you get some hydrogens, you get some oxygens. But because these are covalently bonded, or they're held together in ways that do not require the transfer of electrons, there's no charge to these particles when they dissolve in water, and therefore they don't conduct electricity. We'll do some experimentation in class with this so you can see it a little bit better, but that gives you a general idea of the different kinds of solutes that exist within solutions. So if you would please come in with 2 or 3 clarifying questions, we will discuss them next time I see you. Thank you.